Welcome back. So for the last talk of this Geometry and Tacos meeting, we're lucky to have Yury Ustinovskiy from Lehigh, and he'll tell us about generalized Ricci flow in complex geometry and its solitons.
Yeah, thank you, Fritz. Thank you, everyone, for inviting me. Yeah, it's really a great event. I'm really happy that you made one on complex flows. So, and yeah, I'm going to talk about generalized Ricci flow, and in part, at least in the beginning, my talk is going to overlap with Mario's talk, but I hope it's okay. So let me start with kind of brief motivation about geometric flows and complex geometry in general. Geometric flows in complex geometry. So it's complex geometry. So we start with a complex manifold. M and I will be operator of complex structure integrable. And often we maybe have some extra data. So this could be a holomorphic bundle. It could be a holomorphic Poisson tensor. Maybe holomorphic volume form. So something essential of complex algebraic nature. So something where, for instance, modular equations make sense. And to this data, we can attach some C-infinity flexible data. So by C-infinity data, the typical example would be a matrix. So G Hermitian metric. Maybe you also have something else, for instance, metric in a holomorphic vector bundle. So these are really flexible. So they are structures of C-infinity type. And we would like to find the best one, which describes somehow our underlying geometry. And essentially, in most cases, this amounts to solving certain partial differential equations for those. So we really want to solve PDEs and usually elliptic ones. And unfortunately, in most interesting cases, we don't really have a good method for obtaining solutions. And so flows is sort of a way to bypass it. So, okay, maybe even though we cannot solve it explicitly, maybe we can try to at least make a step towards a solution. So essentially, so why do we care about flows? Care about flows. So the first answer, it's a cheap way to try to solve a PDE, so a seemingly cheap way. So we try to solve an elliptic partial differential equation by substituting it with parabolic equation. On your manifold times some time interval. So if it works, great. So we solved our PDE, and again, in many cases, it gives us some information about geometry. So I mean, the most important example would be Ricci flat, this Calabi-Yau matrix, or maybe Kähler-Einstein matrix, or maybe constant scalar curvature Kähler matrix. So these are all very important. They give you information about algebraic geometry on the underlying manifold. So that's one motivation. So that's why we want to solve flows. So what also happens, even when you can't solve this flow and prove its convergence to the solution of elliptic PDE. So the way flow fails to exist, informs you about geometry. And the typical example, perhaps the most important in this case in the historically the first one, that's how Donaldson's flow for Hermitian Einstein metric on a vector bundle allows to find destabilizing subsheaf. So you get some algebraic information from the failure of Donaldson's flow. So this is two typical examples. So the one more relevant for us today is that often actually, even though we want to solve one partial differential equations, flow somehow by itself gives you a solution to another equation, which on its own happens to be relevant and useful for studying geometry. So sometimes flows converge to solutions of other partial differential equations. So, and specifically how it potentially could happen. So instead of Kähler-Einstein metric on a Fano manifold, we find Kähler-Ricci soliton. So I will talk about it more. So that will be actually the main motivation for us. But that's kind of the high level reason for studying flows. So again, yeah, typical example, not typical, I mean, the most important example, which Mario mentioned in the previous talk, is Ricci flow, of course, Ricci flow. So you flow your metric by negative multiple of your Ricci tensor, and on a Kähler manifold, it preserves the Kähler condition. Preserve the Kähler condition. And so all these advancements in Kähler geometry and the construction of canonical metrics, they are closely tied to the study of the Ricci flow, of course. So, however, if you want to step outside of the world of Kähler manifolds, you immediately run into the problem that this Ricci flow is not very well suited for the study of non-Kähler metrics, specifically because your metric doesn't know anything about your complex structure unless you're on the Kähler manifold. So if you're on the Kähler manifold, complex structures are essentially captured by the holonomy of your metric G. But in general, holonomy of your metric G is not related to your integrable complex structure if it's not Kähler. So we really need another flows on non-Kähler backgrounds. So it has been realized, this fact that we need more flows to try to solve the same problems in the non-Kähler world for the last more than 10 years, and many flows have emerged. So let me mention several of them. So Streets and Tian in 2009 came up with the whole family of flows, which they call Hermitian curvature flows. So they all admit short-time existence. They have some regularization properties, but in general, not much known about generic member of this family. So about the same time, Matt Gill and Tassati, Wynkoff, and others. So they came up with a Chern-Ricci flow. So this is a specific flow which aims at solving Ricci form associated to your Hermitian manifold is proportional to your fundamental 1-1 form. So specifically, you evolve it by negative of rho. So there are good short-time and long-time existence and convergence results on surfaces, on many types of surfaces, but in general, it's not known much about this flow, about what are possible fixed points of this flow and what are possible maybe stationary modular diffeomorphism solutions. So these are in a sense too general. So they are tried to solve the problem which they are trying to solve these two flows. It's too ambitious. So what you might do, you might request some special features from the flow. So what else you might request for the flow to have? What do we want from the flow? So what extra features? So if this problem is too ambitious, maybe we need to consider a smaller problem. And the most important one, the most important class of problems that we're looking for flows preserving partial integrability. Partial integrability. So we don't consider all flows on all non-Kähler manifolds, again, because this family is perhaps too large, but we look at flows which preserve some partial, maybe not Kähler, but something weaker. And in this case, there are several important conditions. So one condition is balanced d star omega equals 0, or equivalently d of omega to n minus 1 is 0, or equivalently you can just say that this Lie form which Mario mentioned is 0. So this is balanced condition. So it really makes sense in dimensions 3 and higher, because in dimension 2 it's just equivalent to being Kähler. And it's quite important because there are plenty of examples, non-Kähler examples of such metrics, and non-Kähler manifolds which do not admit any Kähler metric, but which do admit balanced metrics. So this specific condition was kind of approached by Viduli, Vizzoni in 17. So they came up with what is called balanced flow. So it's a flow of matrix which preserves this balance condition. Again, hopefully it converges to something nice, but again, unfortunately, not too much known about this flow. So there is another condition which is conformally balanced. So we don't consider balanced metric, but we consider metrics which become balanced once you multiply them by appropriate function. And the most important one here is that d of norm omega to the power n minus 1 is 0, where omega is a holomorphic volume form. So this condition, which naturally appears in Hall-Strominger system, and a whole family of flows around this condition was introduced and studied by Picard, Fong, Zhang. So it's an attempt at solving a certain complex nonlinear elliptic partial differential equation by flows methods. So what I'm going to do today, I'm going to focus on a different condition, the one which actually Mario just considered in his talk. So the condition which will be relevant for us is pluriclosed condition. So DC of omega equals 0. So this is called pluriclosed, or sometimes in physics literature it's called SKT, strong Kähler torsion. So its advantage that unlike the previous one, it's linear in your metric. It is related to generalized holomorphic generalized geometry, as was mentioned by Mario in the previous talk. And more importantly, all complex surfaces admit such metrics. All complex compact surfaces admit such metric. So if you want to study complex surfaces, non-Kähler complex surfaces, this is really the flow which seems the most suited for this problem. Again, because it's the best you can expect in general if you step out of the Kähler world, and still you can find such metric on any surface. So this is result of Godeshown. So what Streets and Tian did, they found a specific member of their flow which preserves this condition. So Streets, Tian, they found member of Hermitian curvature flows, which preserves DDC omega equals 0. So they call this flow pluriclosed flow. And then later they discovered that actually this flow appeared sometime before in physics literature in disguise. And this is how I'm going to introduce this flow, and that's how I'm going to actually call it and study it. So let me move to the second part. So what I'm going to do now, I'm going to discuss a flow which preserves pluriclosed condition, and which essentially, again, comes from physics as a modification of the usual Ricci flow in Riemannian geometry. So this is generalized Ricci flow. So we, at this point, let's forget about complex geometry for a second. So we'll have a manifold, we'll have a metric G, and we'll have H. So capital H will be a 3 form, which is closed. So locally, it's a differential of a 2 form, and this 2 form has some physical meaning in certain circumstances of a magnetic field. So we would like to develop Ricci flow techniques for this quantity. So if we don't have H, we have a good geometric flow, the Ricci flow, which is very well studied and suited for many geometric problems, especially in small dimensions. So can we extend it to H? And it turns out that there is a way which at the first glance will look a little bit arbitrary, but it turns out that actually it's a natural way to do it. So definition is we will say that GT HT solve generalized Ricci flow if the time derivative of G is minus 2 Ricci. So if I stop here, it will be just Ricci flow, but we augmented by the torsion by 3 form H. So this is trace G H times H. So this is only a contraction which gives you a symmetric 2 tensor. And derivative of H is d star of H. So clearly, if you don't have H, if H is identically 0, so this equation is vacuous, this term disappears, and all you're left with is just the Ricci flow. But in general, you have more. So far, it doesn't have any relation to the complex geometry, and the the important discovery of Streets and Tian was that actually this flow after gauge modification is equivalent to the Euler closed flow. So actually it is a flow in complex geometry, which has an extension of complex geometry, just like the usual Ricci flow on a Kähler manifold gives you a Kähler Ricci flow. So what exactly happens here? So if MGI is pluriclosed, with H being dc omega I, so twisted differential of omega I, and I recall perhaps that omega I is just GI. No, so it's a 1-1 form which you obtain if you hook in I in your Hermitian metric. So time derivative of I is Lie derivative along the Lie vector field theta I. So you can flow your complex structure by one parameter family of diffeomorphisms. So, and again, and GH solve the equation star. Then along the flow, first G remains Hermitian with respect to I. So it's really a geometric flow in the world of complex geometry, even though you actually change your complex structure by gauge transformation. But this gauge transformation is just the diffeomorphism. And second, you will still have that H equals dc omega I is preserved. Okay. So you get a genuine flow of pluriclosed structures modulo diffeomorphisms. Any questions so far?
Yeah, I actually had a question. So, okay, so equation star, just in general, it imposes, say, DH is 0. Is that true without not in the complex case, but just if you wanted to study star, you would impose DH is 0. Is that right? Yeah,
you need to impose DH is 0 always, yes.
I see. So have you ever seen a flow where they imposed D star H is 0, and then the evolution for DH is just like Laplace of H. So instead it'd be switched, it would be D star DH.
Yeah, I haven't seen such flows. Yeah, actually, perhaps Mario knows better than me.
Yeah, I'd be curious if that one has to do with the balance condition now. If you, because yeah, I don't know this. All right. Anyways, yeah. So yeah. Maybe it wouldn't even have short time existence though. So I don't know. I don't know if it would actually work. But anyways, okay.
Yeah, I mean, you will need to change it, of course. Maybe something D star DH. But yeah, it's interesting. I don't know. So so what I know, again, perhaps you of course also aware with that the specific Hermitian curvature flow, which I considered sometime before, is a conformal equivalent to the flow which preserves conformally balanced condition.
Right. So maybe that could be linked in.
Yeah, but it doesn't have this formulation. So actually,
it doesn't. Okay. It didn't. It didn't connect into that formulation.
Yeah. It's a different.
Okay, that's what I was wondering. Okay.
All right. So we have a genuine flow of balance metrics. So the kind of big issue with all flows. So big issue with all flows are breathers. So these are solutions evolving by scalings / diffeomorphisms. because such solutions, they don't really do anything with your structures. They keep it equivalent in a way. So you scale your metric, you flow your metric, and maybe in this case complex structure and free form by diffeomorphism. So geometrically you don't get anything new, and there is no hope really to solve any PDE, because again geometrically nothing changes. And that's actually the issue for many of the flows which I initially mentioned. So it's not known for many of them, at least in full generality, why they don't admit breathers. And the way you usually prove that breathers do not exist is by getting some integral quantity which is monotonic. So if you have monotonic integral quantity under the flow, that's actually tells you that you have a really nice structure of your flow. And again, for many flows, for instance, for generic flow from Hermitian curvature flows family, it's not known whether there is a monotonic integral quantity. Well, luckily, it's not the case for the pluriclosed flow. So for the generalized Ricci flow, so for generalized Ricci flow, there is a functional which is monotonic, and let me briefly mention it. So what I'm going to talk about is F functional. So this functional is really a modification of Perelman cell functional, which was the key to all the nice properties of the Ricci flow in the 2000s. So what this functional is? So this functional is attached to your metric and free form naturally, and you need some extra quantity which sort of fixes gauge of freedom, and this quantity is function f. So f is a smooth function on your manifold. So it's defined as integral over your manifold of R minus 112 norm H squared plus norm grad F squared e to the negative F dVg. Right, so of course it only makes sense on a compact manifold or on a complete manifold where you can make sense of this integral, so which is not in all cases, so you actually have to be careful. But if you're on a compact manifold, yes, it makes sense. And given this quantity, so you can actually cook up a number associated to G and H only, and this will be infimum of F over all functions of normalized volume. So over all functions, I said this total volume is, say, 1. Right, so it's just a number which you can associate to a metric and a free form. And what turns out to be true in this case, that lambda is non-decreasing along generalized Ricci flow. So that's first part. And second part, if you have slice or maybe 2 times where these lambdas are actually equal to each other, then you happen to be on a very special kind of structure, which is called a soliton. So if you have 2 slices where this number is the same, so T1 less than T2. So then you immediately obtain that GH solves a soliton equation. And that's actually equation which we'll be considering from now on. So this equation, I'll write it as follows. Ricci minus 1/4 trace H tensor H plus Hessian F equals 0, and D star H plus hook grad F of H equals 0. So for sum F, which is infinity of M. Okay. So it sort of rules out steady breathers. So you don't have anything which flows by diffeomorphisms unless it just flows by a gradient of F for a fixed function F. So basically it gives you immediately all the structure about breathers which you can only hope for. And you have to understand those if you want to apply the flow. So solitons, so what it essentially tells you that along the generalized Ricci flow, your structure flows by diffeomorphism generated by gradient of f. And again, you don't converge anywhere, but these structures already get very nice as is. So they are an appropriate generalization of Einstein metric, I would say. So this is generalization of Einstein matrix. So in Mario's talk, so he considered a little bit different equation where instead of gradient f, you have leaf form, but that's actually this one is the equation which will be relevant to us. And again, I'll just mention the obvious thing. If h is identically 0, of course, you don't have second equation, you don't have this term, and you just get usual steady Ricci solitons. All right, and so these are the structures which we're going to discuss from now on. Any questions about this equation? So let me give you one example. So this is S3 cross S1. This is your manifold. And your metric is the round metric on S3 plus the standard metric, the metric on the circle. And your H will be the volume form of your three-dimensional sphere. So it turns out, and F is just identically 0. So this will be solution to this equation star star. Of course, in this example, there is no complex geometry, but you can very easily to put it on if you remember the example from the previous talk. So this is actually structure corresponding to Hopf surface, so which is C2 minus the origin, quotient by contractions. So Z is equivalent to 2Z with metric G given by DZ1 bar plus DZ2 times DZ2 bar over Z1 squared plus Z2 squared. Okay, so this is a pluriclose metric, and if you look at it through this lens, well, that's exactly the soliton which you get. Well, that soliton is not very interesting because f is identically 0, and actually you can prove more. You can prove this is, in a sense, the only non-obvious example of such soliton. So this is theorem of Godeshon and Ivanov. Ivanov from 97. If MGI solves the soliton equation with f identically 0, then either M is Calabi-Yau. Again, it's not interesting. The classical Kähler-Calabi-Yau, perhaps I should say, to distinguish from non-Kähler Kähler-Calabi-Yau. So that's not really something new. It's just, again, K3 surface or a torus. It's in 4 dimensions. Or MGI is isometric and biholomorphic to the example above, to the Hopf example above. up to scaling. So you get sort of rigidity, actually. It's interesting. If you're in Calabi-Yau case and Kähler case, well, you have actually a whole module of Calabi-Yaus. But if you say, okay, I want non-Kähler example, you get a single one, just this. Okay, sorry, I should be a little more careful. So it's definitely isometric, and by biholomorphic, I have to be a little more careful. So it's biholomorphic to Z1, Z2 is equivalent to alpha Z1, beta Z2, where norm of alpha equals norm of beta. Alpha, beta are complex numbers. So this is a contraction so that the metric G descends to the quotient. So you don't have any interesting examples. So you have actually this one round sphere times S1 with an appropriate complex structure on it. So you might ask, okay, can I capture some complex geometry of these spaces by considering maybe more general solitons? So specifically, what I want to observe that there are more general Hopf surfaces. There are more general. Specifically, you can take C2 minus the origin. You can quotient it by similar contraction, alpha Z1, beta Z2. But you now allow your alpha and beta to be of different modulus. So you take this Hopf surface, you can cook up a pluriclosed metric on it. So what happens if you run the flow? Will it converge to something? If it will converge to something, will it converge to a soliton? And can you construct such a soliton explicitly? And it turns out you can. And actually, the behavior of the soliton will capture the different features depending on whether norm of alpha equals to norm of beta or if it's smaller. So theorem. This is Streets and myself. So let me call this manifold M I alpha beta. So M I alpha beta admits a pluriclosed soliton with non-constant f, function f, unless norm of alpha equals norm of beta. So I want to kind of to stress it that actually the behavior of soliton captures something about complex geometry of the underlying manifold. So complex geometric properties of the underlying manifold tell you about what type of solitons it admits. So let me mention a little bit the strategy of the proof. So strategy. So strategy of the proof is fairly straightforward. Is that you actually can find solution among matrix of maximal symmetry. And the maximal symmetry on this space is the torus, three-dimensional torus symmetry. And this just reduces problem to ODE. Problem to ODE and gives uniqueness. Among invariant metrics. So that's nice. That's an explicit construction. The question is that it still doesn't give you a classification. So there are many open questions related to pluriclosed solitons which are still there. So let me mention several of them. So first, I mentioned a conjecture, which I mean, it's almost certainly true. We don't have a method to solve it. Maybe actually what Mario told in the previous talk is instrumental to proving it, but we don't know it yet. So you can cook up a different type of Hopf surfaces, not the one which I described above. So you can take C2 minus the origin, and you can contract it by a linear transformation like this. Alpha 0 alpha and 1 here. So it's like this Jordan cell. So alpha is a complex number of norm less than 1. So conjecture that this manifold does not admit pluriclosed soliton. Does not admit pluriclosed solitons. So, I mean, we haven't been able to construct them, but there is a strong indication that these do not admit, and motivation why we expect it to be. So we expect it to be related to the stability of this vector bundle Q, which Mario mentioned in his talk. So even though in this case you will not have Hermitian-Einstein metric on Q, you will have some weighted Hermitian-Einstein metric if you're in a pluriclosed soliton. And we expect that, again, this stability will give you some obstruction. But again, it's far from being clear why it should be true. So another question, perhaps simpler, but still we don't have full understanding of it. So is to prove uniqueness of solitons on Hopf surfaces without maximal symmetry assumption. So we have the proof with assuming maximal symmetry. If you don't assume it, we don't know. And the pluriclosed soliton, for all we know, they might not be unique. So now, yeah, I'm slightly slower than I expected to be. Maybe let me briefly really mention about generalized Kähler structures. Generalized Kähler structures. So we have all Riemannian manifolds with torsion tensor H. So inside we have pluriclosed stuff, right? So these are pluriclosed. So essentially these are MGI such that H is DCI omega. Right. So inside this part, you have actually even smaller part, so which is I call GK. So let me explain what those are and why they're relevant to us. So GK are quadruples of MGIJ. So these are two complex structures. So two complex structures such that these separately are pluriclosed. MGI and MGJ are pluriclosed, and DCI omega I equals negative DCJ omega J. So they have opposite torsion. So this type of structures actually appears separately in different circumstances. I'll just mention the work of Gates, Hall, Rocek. So they actually have this in this formulation, which I just mentioned. And Hitchin, Gualtieri. So they have a different view of this as coming from generalized geometry. So this is something called generalized geometry. But the point why I'm bringing these structures is that generalized Ricci flow preserves the space of GK structures, generalized Kähler structures. So whenever you have a soliton, you can consider pluriclose soliton, so the ones which live here. But you can also consider generalized Kähler solitons. And since you have imposed more structure, you expect to have more ways to get classification and construction results of those. And so I mentioned just one theorem in this realm. So this is Apostolov, Streets, and myself, is that generalized Ricci solitons on of surfaces are unique and are all obtained by extending solitons of Streets and myself. So we have pluriclosed solitons on Hopf surfaces, and if you want to put more structure on it, if you want to put generalized Kähler structure and classify solitons like this, actually you can do this, and all generalized Ricci solitons, they are actually go from there. So in this case, we have answered to that uniqueness question, and we actually have answered to the non-existence question on this Jordan cell Hopf surfaces, but we don't have this for pluriclosed solitons. And again, I think it's an interesting open question to investigate. So I think I'm out of time, so I'll stop here. Thank you all for your attention, and I'm happy to take the questions from you.